Assalamualaikum and hi there. We are still in chapter 5 on specific chi-square tests. In this part 3, I will share with you the second specific chi-square test covered in this chapter, namely independence test. Let's proceed to the next slide to find out how to formulate the null and alternative hypothesis in an independence test. Before we learn how to write the null and alternative hypothesis for an independence test, let's look at the following learning objectives on independence test. At the end of learning this topic, you should be able to calculate the expected values denoted by EIJ in an independence test. You should also be able to calculate the chi-squared test statistic value using the correct chi-squared formula specific for independence test. And finally, you should also be able to perform the independence test according to the standard statistical testing procedure. To understand an independence test, let us start with this simple example. Suppose a set of data related to two variables x and y are summarized into a 2x3 contingency table as follows, where x is called the row variable with two subcategories and y is called the column variable with three subcategories. Please note that x and y are only generic notations and the position of x and y can be flexible. However, when we mention the contingency table, usually we will mention the row first, followed by the column. Therefore, in this example, we have a 2x3 contingency table where the number of rows denoted by R is 2 and the number of columns denoted by C is 3. Generally, we can have an R by C contingency table. The elements or entries in the table are the frequencies or the number of subjects that have the two characteristics or two subcategories at the same time. These frequencies are also what we call the ijth observed values denoted by Oij for ith row and jth column. For example, the value 4 in the second row and first column here is the value of O21, which have both x2 and y1 characters, whereas the value 5 in the first row and third column here is O13, which is the observed number of subjects, which have both characters x1 and y3, and so on. The question is, are the row variable x and the column variable y independent? Let's learn the general procedure for an independence test to answer this question in the next slide. To test whether two variables x and y are independent or not, we still need to follow the conventional or general statistical hypothesis testing procedure where the null and alternative hypothesis must be stated clearly. The choice of test statistic should be determined and calculated correctly. The decision rule or rejection criterion must be stated explicitly, and finally the decision and conclusion on whether the two variables are independent or not must be written clearly. For an independence test, under the null hypothesis H0, the row and column variables denoted by x and y respectively are assumed to be independent, whereas under H1, the two variables are assumed to be dependent. Decision rule is to reject H0 if a chi-squared test statistic is greater than a right-sided critical value, which is a chi-squared value at the whole alpha and new degrees of freedom. Notice that we are still using a chi-squared test statistic as the appropriate test statistic for independence test, and we only have one critical region and one critical value located at the upper tail of a chi-squared distribution. Now, what is the definition of chi-squared test statistic in an independence test? It is defined as the sum of squared differences between Oij and Eij divided by the respective Eij sum over all ith rows from 1 to R and jth columns from 1 to C. This formula is stated in the statistical table booklet, page 3. Notice that the test statistic formula looks very much similar to the chi-squared test statistic formula for a goodness of fit test, where both test statistics measure the discrepancies between the observed and expected values. However, in goodness of fit test, you only sum the discrepancies across K classes, whereas in independence test, you sum the discrepancies across R rows and C columns for an R by C contingency table. Now the final step of an independence test, which follows the conventional procedure, is to state the correct decision and conclusion regarding the independence between the two variables x and y. Now, what is the value of nu, which denotes the degrees of freedom for an independence test? How are we going to calculate the expected values Eij that appear in the numerator and denominator of the chi-squared test statistic formula? Let's find out the answers in the next couple of slides. Recall the decision rule in an independence test is to reject the null hypothesis H0 if the chi-squared test statistic is greater than a chi-squared critical value at the whole alpha and nu degrees of freedom, where the chi-squared test statistic is given as follows. Now, what is the degrees of freedom nu? Let's look at the list of important notes here. The degrees of freedom nu is defined as the product of R-1 and C-1 for an R by C contingency table. As we know, R is the number of rows or X subcategories, whereas C is the number of columns or Y subcategories. Oij is the observed value or actual frequency in the ijth cell of a contingency table. Oij can also be denoted as nxi intersect yj, which represents the number of subjects which have both xi and yj characters at the same time. The notation eij represents the expected value in the ijth cell of a contingency table. Unlike in a goodness of fit test, where all expected values have to be at least 5, in an independence test, we do not have any constraint on the expected values. That is, Eij can take any value and we do not combine any cell if Eij is less than 5. How to calculate the expected values Eij in an independence test? Recall that Eij is the expected value of the ijth cell of an R by C contingency table. By definition, the expected value is the total frequency or the sample size n multiplied by a probability value p. So for a contingency table, the expected value of ijth cell, denoted by Eij, is defined by the following expression where n double dot is the total frequencies of all cell values or a grand total, which should be the same as the total observed values. You should check later that the total expected values must also be the same as the grand total. The notation Pij is the probability of xi intersect yj, or simply Pxi and yj. Under the null hypothesis, we assume that x and y are independent. When these two variables are independent, Recall from what you have learned in Chapter 1, Pxi nyj is simply Pxi multiplied by Pyj. But what are these Pxi and Pyj? Pxi is the probability of xi, which by the classical definition is the ith row total denoted by ni dot divided by the grand total n double dot. Similarly, probability of yj is the jth column total denoted by n dot j divided by the grand total n double dot. Replacing Pxi and Pyj in the Eij formula, you can see that the multiplier n double dot is crossed out with one of the grand total expressions in the denominator, which finally gives us the formula for Eij, which is simply the product of ith row total and jth column total divided by the grand total. Back to the simple example that we had earlier in this video, the row variable x has two subcategories x1 and x2, whereas the column variable y has three subcategories y1, y2, and y3. The cell values or the Oij values are given to be 2, 3, 5, 4, 2, and 4. The row totals denoted by ni dot can be obtained by summing up the Oij values for ith row across all j columns. Therefore, n1 dot is the sum of 2, 3, and 5, which is 10, and n2 dot is the sum of all observed values in the second row, which is also 10. The column total denoted by n dot j is the total of all observed values in the jth column across all the ith rows. Therefore, n dot 1 is the sum of 2 and 4, which is 6. N dot 2 is 5 and n dot 3 is 9. The grand total n double dot is the total of all observed values, which is also the same as the row total and the column total given by 20 in this example. Now, if you multiply 10, which is the first row total, by 6, which is the first column total, divided by the grand total 20, you will get the expected value in the first cell, which is E11 given by 3. Similarly, if you multiply this 10, which is the second row total, by 5, which is the second column total, divided by the grand total 20, you will get the expected value in the fifth cell, which is E22 given by 2.5. You can repeat the same procedure to get all other Eij values by multiplying the corresponding ith row total and jth column total divided by the grand total. Having all Eij values calculated, now you can list down the paired values of Oij and the corresponding Eij as shown in the next slide. The values of all Eij are given in the boxes as shown in the following contingency table. The paired values of Oij and the corresponding Eij can then be listed in another table to find the value of chi-squared test statistic as shown in the following slide. Listing down all observed values Oij and the corresponding expected values Eij correctly, pair by pair, you can then calculate the squared difference between Oij and Eij divided by the corresponding Eij for all pairs in the last column. The sum of these last column values is the value of chi-squared test statistic that will be used in the independence test. Please be reminded that there is no constraint on Eij values, where you do not have to combine the Eij values if any of the Eij value is less than 5. Recall the simple example question on whether the row variable x and the column variable y are independent. Suppose we perform the independence test at 5% level of significance. As mentioned earlier, under the null hypothesis H0, x and y are assumed to be independent, whereas under H1, x and y are assumed to be dependent. For your information, the word independence can also mean no association or no relationship between the two variables, which means you can investigate whether there is any association or relationship between two variables using this chi-squared test approach, provided, I repeat, provided that the two variables are categorical variables which have a number of subcategories as discussed earlier. What if x and y are continuous random variables? In that case, you cannot use the independence test approach. Rather, we have a specific approach for testing the relationship or association between continuous x and y random variables, which will be covered in Chapter 7 on simple linear regression. Back to the simple example, the decision rule is to reject H0 if the chi-squared test statistic value is greater than chi-squared 0.05 nu, where nu is 2 minus 1 times 3 minus 1 given by 2, and hence the critical value is chi-squared 0.052 given by 5.9915. As the chi-squared test statistic value was calculated to be 0.9778, which is obviously smaller than the critical value, we can decide not to reject H0 and conclude that based on the sample data, the two categorical variables x and y are independent at 5% level of significance. Please have a look at task 5.3 on page 120 from the Statistics for Engineers textbook. Here, a study was conducted to determine whether students' academic performance is independent of their active involvement in a co-curricular activities. The following dataset was obtained. Use a 5% significance level to conduct the study. If you look at the question, you can see that the data are tabulated in a 2x3 contingency table where the row categorical variable is co-curricular activities, which has two subcategories, inactive and active, whereas the column categorical variable is the academic performance, which has three subcategories, namely low, fair, and good. The aim of the question is to determine whether the student's academic performance, which is the column variable, is independent of the student's active involvement in co-curricular activities, which is the row variable. A very straightforward keyword here. You should perform an independence test. So what do you have to do first? Yes, as usual, you need to state the null and alternative hypothesis. Next, calculate the expected values, Eij. Subsequently, calculate the chi-squared test statistic value and state the rejection rule. Finally, make a decision and conclusion. Now, before stating H0 and H1, you may well calculate the Eij first from the sample data given in the contingency table. Let's proceed to the next slide to see how it can be done. Continue with task 5.3. From the contingency table, you can straightaway calculate the expected values Eij by first obtaining the row total and the column total. Next, calculate Eij for every ij cell by multiplying the ith row total with the corresponding jth column total divided by the grand total. Then you get the following EIJ values stated in the brackets. An alternative way of calculating EIJ is that instead of using the formula for every cell, you can just apply the formula to only two of the cells at any corner. For example, the 2 EIJ at the left-hand corner of the table like this. Why is it 2? It's because the degrees of freedom nu is 2. In other words, the degrees of freedom value can also indicate how many EIJ values that you need to calculate by using the formula. What about the EIJ values in the other cells? Well, the rest of the EIJ values can simply be obtained by completing the table, since we know that the sum of OIJ must be the same as the sum of EIJ, either across the rows or across the columns. For example, if you know the value of E11 is 35, of course, instantaneously you will know the value of E21 by simply taking 70 minus E11, which is 35, giving you the value of E21, which is also 35, without even need to use the EIJ formula. Having calculated and obtained all the expected values EIJ, you can then list down the OIJ and the corresponding EIJ pair by pair in another table like this. Make sure you check that the pairs of OIJ and EIJ are all correct. Next, calculate the squared difference between OIJ and EIJ divided by EIJ for every pair of OIJ and EIJ. You do not have to worry if EIJ is less than 5 because this is not a constraint that you need to fulfill in an independence test. Summing up all values in the last column, you will get the chi-squared test statistic value, where in this task 5.3, the chi-squared test statistic value is given by 2.0168, which is correct to 4 decimal places. Once you calculated the test statistic value, please do not forget to write down the null hypothesis H0 and the alternative hypothesis H1. In this independence test, under H0, the two categorical variables, which are the academic performance and active involvement in the co-curricular activities, are independent, whereas under H1, the two categorical variables are dependent. At 5% level of significance, the rejection rule is to reject the null hypothesis H0 if the chi-squared test statistic value is greater than the right-sided critical value chi-squared 0.052 given by 5.9915. What should the decision and conclusion be? Let's find out the answers in the subsequent slide. Let's look at the decision and conclusion that you can draw for this task 5.3. The decision is, since chi-squared test statistic value is 2.0168, which is smaller than the critical value 5.9915, we fail to reject H0. What does it mean when we fail to reject H0? This decision leads to a conclusion that at alpha equal to 0.05 or at 5% level of significance, the students' academic performance and their active involvement in co-curricular activities are independent. Alternatively, you can also conclude that the sample data do not provide any strong evidence at 5% level of significance that the two variables are dependent. I believe this independence test is quite straightforward and easy to follow. Before I end this topic, let's check on this topic's learning objectives. At the end of learning this topic, you should be able to calculate the expected values EIJ for every cell in an R by C contingency table correctly. You should also be able to calculate the chi-squared test statistic value using the correct chi-squared formula specific for independence tests, which is available in the statistical table booklet page 3. Finally, you should also be able to perform the independence test according to the standard statistical testing procedure, which include the steps on H0, H1, rejection rule, decision, and conclusion. That's it for now, guys. I'll see you again in the last topic of this chapter 5 on homogeneity test in part 4 video. Until then, Assalamualaikum warahmatullahi wabarakatuh and see you again very soon.